Hello everyone, and welcome to this Chem Safety webinar online as part of the Safety 360 conference. My name is Sam McGee, and I'm an occupational hygienist. I've been working as a hygienist for the last 7 years at Chem Safety. Today we're going to cover a range of dust exposures encountered in the workplace and how to control them. We're going to pay particular focus to silica exposure and the silicosis that results from it. So just let me share my screen now. So, as I was saying earlier, shielding your workers from silica dust, asbestos, and other environmental contaminants. So you may be asking yourself, what is an occupational hygienist? What do they do? To put it really simply, they're health and safety professionals that do all sorts of things. They mainly deal with the exposure to hazardous substances, whether it be through anticipating the substances, recognizing the hazard they pose to workers, evaluating the hazard they have, communicating the hazard to all parties involved, and coming up with control methodologies to reduce the hazard. So we do this for a range of exposures to hazardous substances, whether it be chemical, physical, or biological agents. We then determine similar exposure groups, or SEGs. These are groups of workers who are exposed in a similar pattern to each other. Therefore, we can do broader control measures that affect a group of workers as opposed to the individual. We consider the health concerns of those workers and potentially figure out other forms of exposure they may be exposed to because of those health concerns. We measure and or assess the levels of exposure on site. And while doing that, we take lots of observations and we understand those work processes, because often a small change in the work process can significantly change the exposure of the worker. We come up with control recommendations. After those control recommendations, we're looking at ways to reduce the exposure, and if we've been successful, we'll do repeat monitoring or assessment to determine how successful those controls were. So before we get further on to this presentation, I just want to go over some key definitions of some terms I'll be using throughout the presentation, just so we're all on the same page. So workplace exposure standards, or WES. These are guideline levels issued by WorkSafe so that a qualified occupational hygienist can make assessments as to whether the exposure is at levels that are of a health risk to those exposed. However, the WES is not a fine line between safe and unsafe, as individual susceptibility plays a part on whether someone will suffer those adverse health effects. Therefore, elimination or minimization of exposure to the process, to the substance, hazardous to health, must be taken wherever practical. So, this goes along to the story of those people that smoke a pack a day and end up not having any lung respiratory issues at all, versus those that have a couple of smokes in their youth, and by the time they're done, by the time they're 50, they've got lung cancer from the smoking. Individual susceptibility plays a large part. That's why we want to eliminate it as much as possible. Then we get on to some different descriptions of particles in the air. We have fumes. These are very small airborne solid particles. So we may think of a fume as a gas, but actually it's condensed small solid particles in the air. They travel in the thermal vapors, so we think of welding fume or smoke being particular examples of this. Dust is discrete particles suspended in the air. We're not too concerned about dust settled on surfaces, but about the dust that's in the air. And fibers. These are small particles that are long and narrow, which meet a specific length to width aspect ratio. So you think of like a strand of hair, that's a fiber, whereas a piece of sand, that's a piece of dust. So some common particulate exposures that we come across on site in the industry in New Zealand. Crystalline silica, and we'll go into that into a lot more detail today. Asbestos, so we've all heard about asbestos, and it's that toxic substance found in school as you read the newspaper headlines. Wood dust, and in terms of occupational hygiene, we categorise that as to hardwood versus softwood dusts. Metal dusts. A lot of metals have toxic properties, and when you get them into a powdered or dust form, they can be very hazardous. Welding fume, all those welders welding all day, every day, been exposed to the fume from their process. And then anything else that doesn't meet these sort of specific categories comes into the particulate not otherwise classified. And we group that into inhalable versus respirable. So because there are a lot of particles out there, and all these particles are in some way hazardous to your health, but we can't do epidemiological studies on all of them, so we just have to group them into just general dust, and that's what this category is. So inhalable is all the dust that you can breathe in and into your respiratory system. Particles that are too big, we just can't breathe in. And respirable is the smaller subsection of inhalable. Those are the particles that can make it into your lower respiratory system, so they get past your body's defenses, such as the hairs in your nose, etc. So, asbestos. It is a series of naturally occurring minerals. You may have heard of them as white, brown, and blue asbestos, otherwise known as chrysotile, amosite, and crystallite. They're governed by their own set of regulations in New Zealand. So, unlike many hazardous substances, asbestos has its own specific regs, in this case, the Health and Safety at Work Asbestos Regulations 2016. It is a current workplace exposure standard of 0.1 fibres per millilitre of air. Now, I don't know about you, but I find that it's a bit of a weird thing to get your head around. So if we think of it this way, normal deepish adult breath is about a litre. So that means 100 fibres per adult deep breath. That's a lot of fibres you can have every day while you're working and still be at the workplace exposure standard. Asbestos controls are normally managed by asbestos removalists. So you can see here in this picture in the background, these are workers with PPE prior to doing some asbestos removal work. And the highest risk of exposure in New Zealand is often by maintenance and other contractors where the asbestos-containing materials have not been identified prior to them doing their work. Therefore, and due to the historic use of asbestos and the lag period with asbestos-related illnesses, the majority of the 700 workplace illness deaths in New Zealand each year are caused by asbestos. Then we move on to wood dust. So wood dust is generated when wood is cut, sanded, otherwise handled, etc. It's classified into two types for an occupational hygiene perspective, hardwood and softwood. So hardwood is the deciduous trees that have short fibres and higher densities above 0.5 grams per cubic centimetre. Softwoods are the evergreen trees. They have long fibres and single-celled structures, and their densities are below 0.49 grams per centimetre cubed. To put this in perspective, common hardwood species we come across in New Zealand are manuka, what else have we got here? The rata trees, southern beech, kofi. We don't come across hardwood all that much. Compared to softwood species like pine, macrocarpa, totra, martai, remu, they're all softwood species. So the current workplace exposure standard for hardwood is 0.5 milligrams per metre cubed, whereas for softwood it's 2 milligrams per metre cubed. And the reason for this is that most hardwood species are confirmed or suspected carcinogens, and this isn't the case for the softwoods. The softwood workplace exposure standard, however, is proposed to be lowered to 1 milligram per metre cubed in 2022. Another one we come across a lot in industry is welding fume. So welding fume is a catch-all term for the fume generated during the welding process. It's very common to see uncontrolled in the workplace. I've been welding all my life. I haven't had any issues. The current workplace exposure standard for it is 5 milligrams per metre cubed. Now, when evaluating the health risks in relation to welding, exposures to the individual metals, gases, and products of combustion should also be assessed. This is because many of the constituent metals and other relevant substances that may be found in the welding fume have workplace exposure standards that are significantly lower than the 5 milligrams per metre cubed, which is the WERS for welding fume, and may significantly contribute to the health risk. So some examples of this, as you can see here on the slide, copper fume has a workplace exposure standard of 0.2 milligrams per metre cubed, and this is why you've got to be trained in how to monitor for these hazardous substances before you go out and do it. You may miss these subcomponents of the fume that are a lot more hazardous than the general welding fume. Other examples are you come across a lot of hexavalent chrome, which has a very low WERS, welding stainless. If they're welding galv, they're more likely to come across zinc fumes, for example. So you need to have an understanding of the process, what they're welding, the type of method they're welding, whether it's arc welding, MIG, TIG, spot welds, plasma cutting. All these things will vary their level of exposure and the types of substances they're potentially exposed to. Then we move on to metal dusts. So often the welding fume can be in combination with the metal dusts. So a large range of metals are toxic when ground down into dusts or powders. And the sources of these metal dusts can range from a powdered pigment being used in paint manufacture. For example, hexavalent chromium is used in some anti-corrosion paints, to the fabrication of metal products. So when someone's grinding or drilling or cutting or sanding a metal product, they're producing a fine metal dust. And therefore there's a range of workplace exposure standards due to the varying toxicities of the individual metals. Some, like chrome, are a lot more hazardous than others, like iron. Examples, you might find a lot of aluminium exposure in window joiners because they're dealing with aluminium flashings on the window joinery. Whereas someone who is working with cast iron might come across a lot more iron exposure. It all depends on what metals or what elements make up the composition of that alloy. And now, moving on to crystalline silica. So we're going to do a wee case study on this and its exposure today. Crystalline silica, also known as silica dioxide, is a very abundant substance found on the planet. It's found in sand, quartz, and glass, for example. In terms of worker exposure, we're most concerned about it when it's in its crystalline form, quartz, and when it reaches respirable sizes. So you may remember earlier, we have those two categories for dust size in occupational hygiene. We have inhalable and we have respirable. Respirable are those that go down into the lower respiratory system of the human body. So they get past all our body's natural defense systems and make it into the alveoli of our lungs. Respirable crystalline silica is found in many industries, ranging from the making of cleaning products. So it's added as like a flour to, it's more of an abrasive part of the product there, to quarries, so mining aggregate from, to be used in concrete. A lot of crystalline silica comes across there, and even in fabrication of kitchen bench tops. This is what we're going to do a case study on shortly. The current workplace exposure standard for crystalline silica is 0.05 milligrams per meter cubed. So onto our case study, acute silicosis. You may have an engineered stone benchtop in your house. They're becoming increasingly popular, and you often see them in kitchens and bathrooms. They are made by mixing a finely crushed rock with a polymeric resin and then molded into slabs and heat cured. The silica content of the engineered stone is approximately 90% crystalline silica, which is much higher than the natural stone products, your marbles and granites. Workers may be exposed to respirable crystalline silica while cutting, grinding, sanding, and polishing stone bench tops during the manufacture and installation. Accelerated silicosis is one of 3 forms of silicosis that have been recently reported in workers of engineered stone. So it's a new form of an old disease. This hasn't come out of nowhere. Silicosis has been around for ages. What is new is the acute version of it. There have been over 100 cases in Australia associated with engineered stone benchtop work. As I said earlier, those benchtops are made up of 90% crystalline silica, and a disease that can occur within 1 to 10 years of exposure. Previously, the range was thought to be 10 to 30 years of exposure before you'd come up with these diseases. And it's progressive. That means it gets worse. It doesn't get better. There have been multiple fatalities in Australia due to acute silicosis. So what is silicosis? You can see here on the slide, this is a picture of medical imaging of a lung with silicosis. Accelerated silicosis results from the inhalation of very high concentrations of silica dust. It develops in a pattern similar to that of simple silicosis, except the time from the initial exposure to the onset of the disease is shorter, and the progression to complicated silicosis is more rapid. Specifically, nodules increase in size and merge into large lesions, leading to progressive massive fibrosis and ultimately cardiorespiratory failure. So often the only solution for these workers is a lung transplant. So how do they control crystalline silica in the stone benchtop industry? We go through the hazard hierarchy and we go for some of the most effective to the least effective controls. So we've got isolation of workers from cutting. So this is an isolation control. This could be via automation, so we're automating the cutting process, therefore the worker doesn't have to be in the cutting area anymore. Or it can be separating the cutting process, so only one worker is in that area and it's separated from the rest of the manufacturing process. Wet cutting or water suppression is an engineering control. So this is using water to capture the dust and stop it from getting in the air, therefore reducing the airborne exposure of the workers. Extraction, specifically on-tool extraction, is once again capturing the dust in the air before it can get in the air near where the worker is breathing. Health monitoring, so this is more of an administrative control. So by doing yearly, 6-monthly health monitoring, you can, with lung function spirometry, you can see that the worker has got symptoms or is potentially regressing, and therefore you can look at your controls, determine whether or not they're effective, and implement more or remove the worker from that situation and treat accordingly. And then finally, your last line of defense is your respiratory protection, your PPE. This is the least effective of any controls because if this one fails, there's no more further lines of defense. So we go back to when offering controls for clients, the general hazard hierarchy: elimination, substitution, isolation, engineering controls, administrative controls, and PPE. In this case, eliminating the product isn't really possible. We can't, people want these engineered stone bench tops, so someone has to make them. Substitution, potentially you could replace it by only doing granite or marble bench tops as opposed to engineered stone, but once again, that really depends on the market sources there. Isolation, you can separate the hazard from the worker. This can be for barriers of distance or time, as well as physical barriers. In this case, often you'll find that the cutting bay for the engineered stone is moved to a different section of the factory away from the other workers. Then we have engineering controls. So once again, these controls can overlap with each other. The engineering controls can be local exhaust ventilation, automation, i.e. a CNC router in this case, are often what are used on site. Administrative controls, you can use things like job share, so you're reducing the amount of time that people are exposed by going through a job rotation process. Maintenance programs to keep all the equipment serviced up to date so it's in meeting the manufacturer's standards, reducing overall exposure, and good housekeeping. So rather than letting the dust build up on site, potentially being disturbed and increasing the exposure of the worker, you're keeping things clean and tidy and reducing the overall exposure. And then finally, PPE. We've all come across it. It's normally the most common: gloves, overalls, safety glasses, respirators, etc. That last line of physical defense around the worker to protect them from the hazard. Moving on to the more general control principles, it's where we apply these controls and their relative effectiveness. So we can either control at the source, control at the pathway, and control at the person. If we control at the source, it's the most effective. It's stopping it getting into the general airspace and the airspace around the worker. Ways we can do this is normally local exhaust ventilation or water suppression techniques around the source. Therefore, the product doesn't become airborne. If that's not possible for practical reasons on site or cost, we can try and control the pathway. That means the airspace between the source and the worker, whether this be general ventilation or extraction, is often what you see in this area here. And finally, if both of those options aren't practical, we go to that last line of defense: you control the person. This is typically in the form of PPE, and it's the least effective because if it fails, there's no further lines of defense to protect the worker. So, PPE, it's often what we see on site as the cheapest and easiest control. However, when done right, it can be more expensive than other controls in the long run, particularly when done correctly. So to do respiratory protection properly, it's not just buying the worker a mask and leaving them, here you go, leave them to figure it out themselves. The workers have to be trained on how to use a mask. If they have facial hair, they need to be clean shaven in the areas where the mask surface meets their face. They need to be fit tested to prove the mask meets the specifications and actually providing the protection that you think it will. They need to have filters. They need to have appropriate places to clean, store, and maintain their masks. They need to know when to change their filters. You need to have a respirator management program put in place. All these things, they add up on the cost and ongoing over time. They may not be as cheap as some of those other options that you thought were too expensive. There are three main levels of filtration used for particulates and respirators. We've got P1, P2, and P3. So these come from the Australia and New Zealand standards. So P1 is a respirator designed to protect from mechanically generated dusts or particles. So think of got a piece of wood, you're cutting it with a handsaw, that's a mechanically generated dust. That'll protect from wood dust, for example. Whereas P2 is designed to protect from dust from a thermally generated process. In this case, we're talking about welding fume. These dust or particles are generated through the thermal vapors of the weld, and it will protect from those. And P3 is a high efficiency filter. In New Zealand, you can only get P3 level dust protection when wearing a full face mask rather than on a half face mask. You can put P3 filters on a half face mask. They will only provide P2 level protection, because at that point, it's not the filters that are the weak point, it is the mask itself. Now, with COVID-19, you may have heard the term N95 thrown around a lot. That is an American standard. N95 is equivalent to P2 here in New Zealand, and N99 is equivalent to P3. So there are a lot of resources out there to help you understand all this. So you can contact a chem safety occupational hygienist like myself and my colleagues at info@chemsafety.co.nz. We're more than happy to help. Other resources available online to give you a good understanding of what to do is Breathe Freely. This is a program implemented by the NZOHS and WorkSafe and industry, and it's helping reduce areas in particular welding fume and crystalline silica exposure. We have WorkSafe. They have a lot of good resources out there, toolbox talks, fact sheets, things to help you get started. We have the HAZANS register. So this is a society of health and safety professionals that have been approved. They meet the certain standards, so you can go on there, you can put in a topic of what you want, and they can find qualified people that can help you there. And then we have the NZOHS, the New Zealand Occupational Hygiene Society, the Society of Occupational Hygienists in New Zealand, and they have a lot of good resources there as well. So that's it for webinar today. It's been a pleasure. If you have any questions, feel free to contact us. We are more than happy to help.